Welcome to Mastering Continuum Elements in Abaqus. In this mini intro, I'll show you how to choose the right solid elements so your finite element models are both accurate and efficient. First, we'll look at incompatible mode elements. They modify the deformation gradient inside a first order element so that bending is captured correctly and shear locking is greatly reduced. These extra modes are internal to the element, so they don't break kinematic compatibility and they work very well even in nonlinear finite strength simulations. Here you can see the difference. An incompatible mode element allows the deformation gradient to vary linearly across the element, which is what we need in bending. And a standard first order element keeps the deformation gradient almost constant, which is cheaper, but often too stiff and prone to shear locking in bending dominated problems. Abaqus is very careful about kinematic compatibility between elements. Its formulations avoid overlaps, gaps, or artificial holes between neighboring elements. That means your meshes behave like a continuous solid, giving more robust and reliable simulations, especially in complex 3D geometries. Incompatible mode solids often give accuracy close to quadratic elements, but with a cost similar to linear elements, so they are a very good compromise for bending problems. To get stable results. The trade-off is that they are more sensitive to element distortion, so you still need a reasonably good mesh quality to get stable results. This slide shows how element distortion affects something simple like the displacement. As you distort the mesh, the results start to deviate from the reference solution. It's a reminder that even with advanced formulations, we must always control mesh quality and avoid highly distorted continuum elements. For nearly incompressible materials like rubber or plasticity at high hydrostatic stress, standard displacement elements can lock completely. In those cases, you should switch to hybrid elements in Abaqus, like C3D8H, which add a pressure field and handle incompressibility without volumetric locking. So, how do we choose? For bending dominated problems, incompatible mode or second order reduced integration elements are usually a good first choice. For nearly incompressible behavior, go directly to hybrid or mixed formulations, and always check for locking if your deflections look unrealistically small. Abaqus provides element recommendations in the documentation. For example, it points to a specific reduced integration solid for bending, to hybrid options for incompressible response. In this tutorial, I'll follow those recommendations and show you practical examples so you can confidently pick the right element family in your own model. The main message is simple. Element choice is a modeling decision, not just a default. It directly controls stiffness, locking, and the accuracy of your results. By understanding incompatible, hybrid, and standard elements, you can avoid many typical FEA mistakes and get closer to the real structural behavior. Finally, we summarize the element type and integration. First order full integration solids are robust, but may lock, Reduced integration and enhanced formulations relieve locking but need good hourglass control. Shells, continuum shells, and solid lock shells follow similar ideas. The goal is always the same: pick a formulation that represents the physics without artificial stiffness.